In today's homes, comfort and efficiency are necessities, and how you will heat and cool your home are major decisions. Consider this 5,600 square foot home. It costs less than $70 a month to heat.
Well, when I built my home in 2000, I wanted to make sure that I would have very low energy bills because I intend to stay here for a long period of time.
Most of these energy bills are for heating, cooling, and hot water.
Looking at the way energy prices were starting to creep up, I felt that the geothermal system offered the best possibilities for energy savings.
Geothermal energy systems use the natural warmth of the earth to heat and cool your home. Nearly half of the solar energy that reaches the earth remains stored in the ground at a constant temperature of about 50 degrees. With geothermal technology, there are two basic ways to capture and use this heat, with open-loop and closed-loop geothermal systems. Open-loop piping systems are used in rural areas with a well. In other locations, closed-loop systems are most common. They use a piping loop installed underground or in a pond, depending on the size of the property. Each closed-loop piping system can be placed horizontally, vertically, or with a directional bore to absorb the earth's heat and move it into your home. During the winter, a geothermal energy system delivers heat from the earth to a furnace. The heat is compressed to a higher temperature and moved through the home by forced air or radiant floor heating. During the summer, the process reverses. The geothermal energy system removes the heat from the home and deposits it into the cooler earth. The result is a cool, dehumidified home.
Well, the first benefit that we looked at was the cost savings. In this home, our differential between doing a conventional system versus geothermal was about $10,000 more for the geothermal system. I'm spending about $60 more per month in my mortgage, but I'm saving about $110 to $120 a month in energy.
And those savings are pretty typical for homes with geothermal in Michigan.
But then when we looked further into the systems, we found that they're really environmentally friendly. Because we use renewable energy from the ground, we're not having to rely on fossil fuels. And since there's no combustion, it's very safe as well, so there's no risk of carbon monoxide in the house.
Geothermal energy systems are quiet, dependable, and safe. They have few moving parts and require little maintenance.
We get our system checked about once every 2 years just to make sure it's operating at its peak performance. And so far, there's been no problems at all.
Geothermal energy systems also have no outdoor equipment. They maintain a comfortable, even temperature in the home, and they provide efficient, renewable heating, cooling, and hot water.
Well, the number one recommendation is that these systems, through their energy savings, pay for themselves. And it's just a smarter way to use our resources today and not use as much energy for heating and cooling.
Geothermal energy options. How it works. Geothermal heating and cooling works by tapping into the constant heat source that is found 5 feet below the Earth's surface. In the Northeast, this temperature is approximately 53 degrees. Direct exchange geothermal, or DX, outperforms water source geothermal systems by 25% and is the most efficient system on the market. That's because DX does not require electrical circulators, which use additional electricity. DX only requires one heat transfer, and DX utilizes copper piping, which has superior heat transfer properties instead of the plastic tubing used in water-based systems. Our equipment and installation are what separates us from everyone else. We drill our boreholes to a depth of 100 feet. When drilling to 100 feet, we are very likely to encounter moist soil and/or rock conditions, which are preferred for conductivity. Each borehole is drilled vertically and is spaced 7 feet apart. This prevents the phenomenon of ground loop interference. Envision each borehole as a 7-foot diameter cylinder that uses this area to gather the Earth's energy. When ground space is a concern, a teepee-style or slant configuration can be used to reduce the area needed for drilling. Notice the reduced surface area needed at the top of the boreholes. Here's a simplified version of how a heat pump works when heating your home. All heat pumps have a compressor and an expansion valve that manipulate refrigerant. A refrigerant has two phases, gaseous and liquid. Refrigerant works on the basic principle that if you raise the pressure, you raise the temperature. If you lower the pressure, you lower the temperature. This is all done with a compressor and an expansion valve. Let's say the refrigerant starts its journey in its gaseous state and enters the compressor at 30 degrees. The compressor compresses the gas, which increases the pressure and raises the temperature to 160 degrees. The refrigerant travels to a coil where a fan blows across it. The air blowing across this coil absorbs the heat energy and distributes it throughout the home. As the refrigerant leaves the coil, it condenses back to its liquid state and moves toward the expansion valve at 85 degrees. The expansion valve is basically like a dam with a small hole. When the refrigerant passes through the expansion valve, the pressure rapidly decreases and the temperature falls to 20 degrees. It then moves toward the TXV valves. These valves control the amount of refrigerant distributed to each ground loop. The refrigerant is then piped out to the well field and down the vertical boreholes where it begins its transformation back to a gas. As it transitions back to its gaseous state, it absorbs heat energy from the earth and travels back to the compressor where this ingenious process is repeated. When cooling is desired, this process is reversed.
Well, the key component for any of these geothermal heat pumps is to have some interaction with the ground, so it needs some sort of well. One type of well is a closed loop filled with antifreeze that circulates horizontally about 5 to 10 feet below the surface. Or you can install the same closed loop of antifreeze vertically into a well that may go down hundreds of feet. A third option is to have an open loop in which groundwater, not antifreeze, is pumped out of the ground through the heat pump and then returned to the ground. The key for any of these loops, though, is that we're always going to find 50-degree temperature both winter and summer under the ground.
Yeah, but I don't know many people who think that 50 degrees is a comfortable temperature to keep the house in the winter.
Right, but that's where the heat pump comes in. We're going to use the basic refrigeration cycle that we see in every window air conditioner, every refrigerator, even to cool our cars, to use that 50-degree water to make your house comfortable. The water or antifreeze is pumped into the heat pump, and in the winter, the heat is transferred to a closed loop of liquid refrigerant. That refrigerant now goes into a compressor, which uses electricity to compress the liquid refrigerant, turning it into a gas and making it very hot, maybe 130 to 150 degrees. In a typical forced air application, air is blown across the coils of that hot gas, heating the house. The refrigerant is then cooled by the air and it turns back into a liquid, and the process repeats. The same equipment can be used to cool the house in the summer, simply by pumping the refrigerant in the opposite direction.
All right, so I get the theory of how they work, but what do the systems look like?
Well, recently I took a homeowner to see one of these geothermal systems in operation. So we got an email from you curious about geothermal heat pumps, and you're building a new house.
That's right. I just recently bought some property on our lake, and
Great.
I'm in the planning stage of the heating system.
Well, I thought I would bring you here. This homeowner about 6 years ago decided to put in a geothermal heat pump. That's a ground source heat pump. Now most people might know a heat pump because it might have equipment like this on the outside. This is called a condenser. Now when it's in air conditioning mode, heat is absorbed from inside the building into these refrigerant lines and it dumps to outside. When it's a heat pump, it also can reverse, and that actually can be looking for heat from outside to be absorbed into the refrigerant to go into the building. The problem is it gets really cold here and there's not much heat to be had. How cold does it get around here?
It's freezing most of the time
That's
in
right.
the winter.
So now with geothermal, we actually could use the heat that is below our feet, down under the ground. Once you get down to 4 or 5 feet down, it's about 45 to 50 degrees down there. So now you got to figure out how you're going to collect that energy. So you could put a bunch of pipes down 5 feet down to collect the energy. You could do a closed loop, but this homeowner chose to put a well like this. This is actually about 400 feet down. At the very bottom of it, there's a pump, and it's going to take that water and pump it up and go into the house where we can use it to heat the building. Let me show you. The pipe actually comes into right here. So here's that 50-degree water that's going to come in. It comes across the ceiling, and now it goes right over to here, and it comes down into this heat pump right here. Now inside this heat pump, there's a heat exchanger, And there's the basic refrigeration equipment that we see in every refrigerator or air conditioner. So what happens is that heat exchanger picks up that 50-degree temperature, and now it gets absorbed into the refrigerant. Now when that refrigerant gets compressed and get really hot, that 50 can be 120 or 130 degrees. So now that hotter refrigerant comes over here, and now when that air blows across it, it can actually heat the air enough to heat the building. Refrigerant gets cooler, goes back to that 50-degree water, picks up more temperature, and the cycle continues. In the summer, it's just the opposite. It picks up heat from inside the building. Now it takes it back and it dumps all that heat down under the ground and back into another well outside.
A new era of home comfort has arrived with geothermal heating and cooling. While the name may sound space age, the technology is down to earth. Watch this short video from Ingram's Water and Air to find out more about how you can heat and cool your home and lower your energy costs using the natural heat of the earth. So, how does it work? A geothermal heating and cooling system, sometimes called a ground source heat pump, works on a simple premise. The earth below the frost line, usually about 4 feet down, is a constant temperature of about 50 degrees year-round. During the winter, heat can be taken from the ground and transferred through a heat pump to the air in your home. Heat can also be transferred back into the ground during summer to cool your home. How about lower energy bills? Heat from the ground is free, and the only electricity needed is for moving that heat between your home and the ground. A geothermal system can lower your heating bills up to 50% and cooling bills up to 30%. This could mean a payback in as little as 2 to 5 years, and when considering the federal geothermal tax credit of up to $2,000, the payoff is shortened even more. A common and cost-effective geothermal installation method is to use an open-loop or well water design system. In this method, a well supplies both household water and water for the heat pump. Approximately 2 to 3 gallons per minute of well water are needed per ton of cooling capacity, and a 3,000 square foot well-insulated home would typically require 10 to 15 gallons per minute when in use. In an open-loop system, groundwater is supplied to the heat pump by a drilled well with a submersible pump system. If a recharge well is to be used, it should be drilled at the same time as the primary well. When the thermostat calls for heating or cooling, the slow-closing solenoid valve opens to allow the water to flow through the water coil in the heat pump. The clean discharge water is normally piped to a creek, pond, or recycled. Groundwater should be tested for acidity, dissolved solids, and mineral content. Normally, the supply water is tapped straight off the bladder tank from the well, and shut-off valves and flow meters are used to accurately meter the supply water to the heat pump. For more information regarding open-loop applications or geothermal equipment, visit www.betterwayac.com or call 24/7 at 1-800-360-1569.
with the beautiful property that he has here, he has chosen to go with what they call a horizontal dug closed loop system. Basically what you see here is you're seeing a series of pipes that are inserted into the ground, buried about roughly 6 feet into the earth. They are filled with a ethyl alcohol and water solution, about 25% ethyl alcohol to water solution. And this circulates in and out of this ground, again about 6 feet deep, going into the home's heat pump system. And this is the means of heat transfer and cooling transfer for the geothermal system that's being installed here. On the inside of the home, this fluid, again, goes into the system. It goes into the heat exchanger, and from there it's a forced air system that will provide heating and cooling for the home. The closed loop system here, the horizontal that you see inside the trench, very efficient system. Basically, a lot of folks want to understand how you take a cold fluid from the ground and bring it into a heat pump system and create heat or release heat to the ground for cooling purposes. Well, this particular application here is designed for a low loop temperature, about 32 degrees Fahrenheit. So the question is, how do I take a 32 degree loop temperature fluid, bring it into a heat pump, and make 95 degree air coming out of my vents in my house? What actually heats and cools your home and the efficiency factor in your heat pump machine or in geothermal is the refrigerant itself. So this is designed at about a 32 degree loop for the winter time. Where the 32 degree loop goes into the home, it'll actually add about 3 degrees of temperature to the refrigerant as it becomes a hot gas, and then will then go to your heat pump's evaporator and create heat of about 90 to about 95 degrees Fahrenheit, which is very comfortable and can heat a house very comfortably. Here we are at the manifold entrance, where all of the loops that come from this horizontal field, they enter into what we call a 2-pipe reverse return manifold. So basically, you'll see that this is a supply pipe, and this one over here is a return pipe. Both of these pipes go through this offset trench and into the basement of the house, where it will be connected to a circulator module system that'll tie into the heat pump and circulate through these loops. These pipes are all hooked up in a fashion so that they're, in this particular application, everything is on the loop field side, on the 3/4 inch pipe, which is all the small pipes you see coming into this 1.5 inch manifold header. All of these loops are exactly 600 feet in length. Extremely critical to make sure that your loops are all 600 feet, that you don't have one loop that's 580, one that's 600, one that's 540. The reason for that is you won't get even circulation through the manifold system going into the house. We want to make sure that we are optimizing the amount of fluid that's going through all the loop and getting all the recovery from the ground that we possibly can here. So these lines, again, come into this manifold. Every one that supplies out, that goes out first, comes back last on the return header. That's where I came and said the 2-pipe reverse return in the very beginning. Then these lines are 1.5 inches, which is enough water and fluid volume, with the ethyl alcohol volume. 1.5 inches is what we needed on this particular application to carry all the fluid that runs through this loop for the horizontal system. Now the pipes that are coming from the loop field here that go into the 2-pipe reverse return manifold system, they are tied in with geostab adapters. Very tight fit. Once they're pressed inside, you're going to need a Chevrolet pickup truck to pull them apart. After they're underneath the ground, they're well buried, sealed, and good forever. Now, this is again a horizontal geothermal closed loop system. Basically, when you're doing a horizontal system, you can see that you need a tremendous amount of land mass in most cases to be able to do a system like this. Just to give you a general rule of thumb, if you had a home that was fairly well insulated, that's about 2,500 square feet, you would have about what they call roughly a 5-ton system. Now again, that's not the way to properly size a system. It's a basic rule of thumb to give you a rough idea of how to go about the thinking process and what needs to happen to do this. So that's about the size of the home that we're at today. And so this particular application here, we are using, again, straight pipe runs in the ground, not what they call slinky loop systems, but straight pipe runs. And we wanted in this particular application to have 600 feet of pipe run per ton of equipment. So in this case we have 5 independent trenches. All of these trenches are 8'6" wide by 100 feet long in depth. And then the area in which I'm standing is what we call an offset trench, where all of the loops come in and tie together. So if you take a look here, you'll see that the amount of land mass that you would need for this type of a trenching system, which this particular job lent itself to quite a bit of open space, beautiful digging soil here. We didn't hit any ledge on this particular instance, and I'm 6 feet in the ground as we speak. So this particular application here is about 9,000 square feet of area. That's due to the trenches. Now, sometimes you can take, in another way you can look at the horizontal system is if you have this same particular 5-ton house, which also could have been done here as well. But in this application here, we could have used, for the same amount of pipe run, we could have used a 55-foot by 100-foot long pit, which means you wouldn't have had trenches. It would have been just one big open pit, much like you're digging a foundation for your home. And then the pipe runs could have been laid in and out of the pit with about 20 inches of separation between those particular loops. If you don't have an application or a piece of property that allows itself to do this, then your choice would be to go with a drilled vertical closed loop system. This particular application had plenty of land mass, so thus they were able to do it very easily. It took roughly about 2.5 days to excavate this out, about 1 day for the, actually right now about a half a day for the guys to lay the loops down, put everything together. Everything is tied into the building, and as we speak, they are pressure testing and doing what they call a hydrostatic test with water and air to make sure that there's no leaks. And off in the distance, the excavator is standing by, waiting to backfill. This job was performed by Ultra Geothermal Incorporated. My name is Darren Rice, Geosystem Designer and Field Manager here at Ultra Geothermal. The excavation work and the loop work was done in partnering with our company, with Comac Pump and Well Company of Kingston, New Hampshire. We do work very closely with Comac when it comes to these jobs. The two of us have really got a good relationship and have a good understanding of what needs to happen with these types of systems, and always good to have a great working relationship.
Hi, I'm Sean.
And I'm Ryan.
I'm Nick.
We're with Comac Pump and Well, just finishing the new installation of the horizontal closed loop project at the Fountain residence.
Well, now we're inside here in Newmarket, and this is basically what you're looking at here. This is what they call a split geothermal heat pump. The heat pump contains a compressor, condensing section, etc., heat exchanger that gets connected to the loop field. And this is what takes the energy from the ground in the refrigerant circuit and moves it over here to this furnace system. We are going to be tying this geothermal heat pump here into this gas furnace. So this is the gas furnace. This is an evaporator coil. So the geothermal heat pump is going to connect from here to this evaporator coil. So your heating and cooling via your refrigerant will be done inside here, and we will be using the electronically communicated motor, or ECM motor, from this as an air handler to put the heating and cooling into the home. Now, the gas will not be running during that portion of time when the geothermal is on. The reason why there's a gas furnace here in place of just a straight geothermal heat pump is the gas furnace acts as a forgiving source to power outage. In a typical geothermal heat pump, you'll have backup KW heating, which is an electric strip heating element. So basically what will happen is, rather than using, if there is an emergency purpose, so to speak, or extremely cold temperatures, then what will happen is, if the geothermal for some reason does not keep up with the load in the house at that particular point in time, the gas furnace can now come on and work in conjunction with the geothermal. And that's done strictly through your thermostat. But the better benefit to this system, and why this is being done here, is generator sizing. So for those of us who live here in New Hampshire know that power outages have been very prevalent in the last 5 to 10 years. When you install a geothermal heat pump into a home and you need a backup generator or size a generator for that geothermal heat pump, the problem you have is you need a very large generator because the compressor runs at what they call a very high locked rotor amperage, thus creates a very large generator to run the house. So in this particular application, when there is a power outage, the generator can be sized much smaller, which is much more cost effective to handle the whole house, and the generator will now work with this gas furnace. So when you lose power, the gas furnace now can run off your generator. So a lot of benefit to going with the system. Efficiencies are the same as long as you match your geothermal heat pump with the proper evaporator section. You achieve the same efficiencies on when you're running your geothermal, and the benefit of having the backup gas. The generator company who had originally sized this house for a generator to run the house, including with a standard geothermal, said that the generator was going to need to be between a 22 and 24 kW generator at a cost of about $10,000. But by doing this instead of the straight geothermal and having this as the backup and run off the generator, they were able to reduce it to a 12 kW generator at a rate of about $3,000 to $4,000. So this is about a $1,000 upgrade versus a packaged unit when you're going to install something like this. However, that's a significant savings or upgrade cost to spending that additional money for the generator. Okay, here we are a couple days later. Get to start to see things starting to get connected to the geothermal system. I'm here along with Bill from Comac Well and Pump, who's working with us doing the closed loop horizontal system here. And basically what we're doing here is we now have the loop field from the outside, which is now connected to an indoor purging manifold. Bill here has got a what we call a pump cart, which is what you use to pump water into that loop field as well as mixed glycol solution. Correct. In this particular case, it's a product called CP Therm, environmentally safe product, and that is all going to be inserted into the loop field through this purging station. So everything here is done in the process with the pump running. Everything's in the process of filling up in the loop field. Eventually Bill's going to have water coming into the building here eventually, and then we're going to be able to add glycol and mix it all up and filter it throughout the whole system. Not much to explain here other than we have an inlet and an outlet, a couple of purge ports for the pump cart to come into, to in and out fluid. So basically with this being shut here, basically you're just filling the field right now.
Right, just bleeding all the air out and adding water to get it full of water.
And then once we get to that point, then valves will get opened up, and then the fluid solution will then be filled into the heat pump system and connected fully with the field. Good demo.
Okay, you can see this is what happens when you put in an open loop and you have a corrugated tile. It gets plugged up with tree roots and then it doesn't work, and then you got to pay to have it redone. It'd be cheaper just to put in a closed loop to begin with and get it over with. You can see that the root has completely filled that tile, so there's no longer any drainage. And look at all that water that's going to back up into the basement. Okay.
Putting in a geothermal system in my house today. It's GeoSmart Energy. And here's my house. It's a single dwelling house in Waterloo, Ontario. Let me show you how it's done. Okay, here we have Peter. He is laying out pipe, ready to install. And he's going to be doing the drilling. He's going to be drilling 10 holes, each at 80 feet deep. And that makes 800 feet for a 4-ton geothermal heating and cooling system. He's laying out the pipes now so that he can put the U-joints on the end to insert the pipe into the ground. Now here you see Peter is fusing the PE100 geothermal pipe, putting a U-bend on the end so that 2 sections will go down the pipe. Peter now putting 80 feet of pipe down into the hole. He's got to force it down there. And once that pipe is all the way down the ground, he's going to pour a cement-like grout solution down the hole, which will seal it. This is a pretty physical job, though. This is hole number 3. Originally we were hoping for 4 holes at 200 feet each, but now we're going to have to do 12 holes at 80 feet each because we can't get down to 200 feet. Now this is where Peter is inserting a grouting pipe. That's going to go all the way down to the bottom and insert the grout from the bottom, and then as it fills up, he'll pull that pipe up. Alright, so here you can see that Mark is excavating the loops, and he's going to be digging down 5 feet so that he can tie the tops of these loops together. And then once they're all tied together, they're going to go to a header that's, instead of 3/4 inch, it'll be 1 1/4 inch, and that will go into the house. So it'll be 2 pipes going into the house. So here we see Mark has finished the trenching and is now starting to tie together the geothermal pipe. Once they're all tied together onto the header, which goes into the house, he will then backfill these trenches, and hopefully I will have a lawn again. So it's a bit hard to see, but the fusion is done in these 3 pipes. And Mark's working on the other ones on the other side now. Mighty muddy down here in the ditch. Oh, foot's getting stuck. So here's a fusion we just did. It's just cooling down. So that's a reducing T-valve. There's Mark in focus. It's going to do some more T-junctions down here. So here we are in the mud. And it's pretty sticky. Doing some fusion. I'm holding the fusion iron and it's hot. And we have electrical and we got water. Always a good combination. Mark's holding the fused pipe for, what is it, 60 seconds? 30. And that's one more connection done. It's day 2 of the geothermal tie-in, and our trenches are being filled back in now. All of the geothermal pipes have been connected with a little bit of extra left over that's going to go into the house. It'll go in somewhere around where the barbecue is there. So all of the slurry is now filling the trenches, and all of this is being backfilled. So now you can see that most of the other trenches have been closed in, and one leading to the house has been dug, and Mark is just clearing away a space so that the pipe can go right into the house. So what are you doing right now? Why are you doing that?
Because I'm the pipe.
Aha.
In the house.
Why did you pressurize it?
Check the leak.
Aha. So the whole loop is pressurized right now, or at least was pressurized, and Mark's just let out all of the air, or letting out the air, and then he's going to cut it just before he puts it in to the hole, which is right there. One down, one to go.
Two down already.
Alright, we got the final filling in. And then everything will be done besides hooking up the geosystem inside. Okay, so we're on the last stage of installing the geothermal heating and cooling system. Here's the two pipes coming into the house from the loop. And we have to hook them up to a pipe, two pipes going across through the ceiling over and down to the heat pump in the other room. Which we put in yesterday. Here it is. The GeoSmart Premium G. And we've already connected the flow center. And that's going to the heat pump. So this is the pump that controls the flow from the loop. So Mark is doing some fusion on one of the last elbows that will be connecting to the loop on the outside, which goes to the 12 holes that were drilled, each at 80 feet deep. And all of these pipes are insulated so that the heat is not lost. When it comes into the house. Alright, so we're doing the last fusion to hook up a geothermal loop. And once this is done, we'll be able to do some, we'll be able to fill the loop with water. Okay. So we're adding the alcohol, the ethanol, to the loop, to the flush cart. And we're ready to flush the loop. Once the flush cart is turned on, that will circulate the ethanol into the loop through those two green pipes that you can see, going through the flow center. And that will mix the existing water that's in the loop. It'll also take out any debris and that's existing in the loop, any dirt that got in there during the installation of the loop. And we can also top up the loop with water. So how do you know how much ethanol to put in there?
By the loop size. So much for every foot of 3/4 and
So you've measured, that tank is measured?
Yeah.
That tank is measured and you've got it measured exactly to how much we need to put in there?
Yep.
Okay. So now we have some water going in that's going to top up the loop. How do you know when it's full? So what's happening now?
get the air out of the loop.
So why is it bubbling?
Those are the air bubbles that are in the loop.
So when it stops bubbling?
And that's all liquid coming through, and then you'll see more air come through.
So how long should we wait until the bubbles are clear? Like until...
It ranges different ones. Sometimes it's 10 minutes you can be done. Sometimes
why is it white now?
That's the ethanol foaming up.
Alright.
There's a big... Well, she'll drop down. You got a bit more water.
So that blue will mix in a little, it'll become a little clearer, right?
Yep.